Hello and welcome back to Vector Flow, guys. In today's video, we are going to talk about how networks actually learn. First, here's a quick recap. In the last video, we built a neural network from scratch. Layers, weights, activation functions, forward pass, and we just got a prediction out of the other end. But we never actually trained anything. The weights were random, the outputs were garbage. So the real question is, how does a network go from random noise to something that actually works and makes sense? Well, this is what this video is about, training and how networks learn. There are three pieces. First off, we measure the error, then we trace it back through the network, and finally we update the weights. And these three steps combined are how every modern AI system learns. First, we need to know how wrong our network is, and that's the job of the loss function. It takes the prediction and the true answer and produces a single number, how bad we are. The higher that number, the worse the network is doing. Two loss functions can cover most cases. First off, we have mean squared error, or MSE, which squares the difference between prediction and truth for every example, then averages. Squaring does two things. First off, it makes everything positive, and it punishes large errors much harder than small ones. Being off by 10 is not twice as bad as being off by 5. It's 4 times worse. Some things worth noting about it is that it's differentiable at every single point, so we can get clean gradients on our way back. And it's sensitive to outliers because squaring would amplify them, obviously. However, it is still the default for regression problems. We then have mean absolute error, or MAE, which takes the absolute difference instead. It's more forgiving on outliers. So let's say if your data has a few extreme examples, you don't want dominating training. MAE will handle those much better. It's more robust than MSE, but it is not differentiable at 0. Either way, we now have one number representing how bad the network is, and the goal of training is to make that number as small as possible. Alright, now let's talk about gradient descent, but first let's build some intuition before anything else. Think of the loss as a landscape. Every possible combination of weights in your network corresponds to a point on this landscape. The height at that point is your loss, how bad the network performs with those current weights. Your job is to find the lowest point in that landscape. If you start at the random point, which you do, because weights are random at first, you need a way to navigate down. You can't see the whole landscape. You can only feel the slope right where you're standing. That's the core idea. Feel the slope, step downhill, and repeat. But to step in the right direction for every single weight in the network, and there can be millions, you need to know exactly how much each weight contributes to the loss, and that's what backpropagation computes. And here's the problem that backpropagation solves. Our network makes a prediction. We compute the loss, but the loss depends on the output layer. The output layer depends on the layer before it. The layer before it depends on the one before that, all the way back to the first set of weights. So how does changing a weight in layer 1 affect the final loss? Well, to find that out, you work backwards. You start at the loss, you calculate how it depends on the output layer, and then you calculate how the output layer depends on the layer before it, and so on, chaining those dependencies all the way back. This is the chain rule from calculus. If A depends on B and B depends on C, then you can compute how A changes when you change C by multiplying the two rates of change together. Backpropagation is just a chain rule applied to the entire network, layer by layer from output to input. Each term is a local gradient at that layer. Now let's make this concrete. Suppose we have a network with three layers. During the forward pass, we compute each layer's as output and store it. Those stored values are important since we'll need them on our way back. At each layer, we store the inputs, the pre-activation values, and the post-activation values of the neurons of that layer. Now, we flip directions. We traverse the computation graph in reverse. First, we compute the gradient of the loss with respect to the output. For mean squared error, this is proportional to how far the prediction is from the truth. This is why mean squared error is so common. The math on the way back is clean and simple. Then, at each layer going backwards, we compute the pre-activation gradient using the activation's derivative. We compute the weight gradient, we compute the bias gradient, and we pass the gradient back to the previous layer. We keep going until we reach the first layer. Every weight in the network now has a gradient, a number telling us exactly how much it contributed to the error and in which direction. Here's a quick note on ReLU. Its derivative is 1 when it is positive, and 0 in all other cases. Very simple. This causes a problem called dead neurons, because if a neuron's input is always negative, its gradient is always 0, so it never updates and it never learns. And this is why proper weight initialization matters. And here's why backpropagation is fast and efficient. The naive approach would compute the gradient for each weight separately, and that's redundant. However, backpropagation reuses every intermediate gradient, taking advantage of those redundancies, and each layer's gradient is computed once and passed backwards. The total cost is one forward pass plus one backward pass, no matter how many layers deep the network goes. There are two main reasons why we use stochastic gradient descent instead of standard gradient descent. The first one is the loss landscape. A neural network's loss surface is not a clean bowl with one minimum. It's full of local minima, points where the gradient hits zero, but you're not at the lowest possible loss. Standard gradient descent can get permanently stuck in one of these, and random mini batches, by introducing noise into the gradient estimate, will kick the optimizer out of those shallow traps. But there's an even more prominent problem, which are saddle points. These are flat regions, like you see on screen, where the gradient is near zero in every direction. It's not a minimum, you can just think of it as a plateau, and the network stalls. The same noise from mini batches helps here too, nudging the optimizer off the flat and back into a descent. The second reason is speed. Standard gradient descent processes the entire dataset before taking a single weight update. On a million example, that's painfully slow, but with many batches of about 30 to 256 random examples usually, you immediately get an update after each batch and take far more steps per epoch, which is one time of seeing the entire dataset. Strictly speaking, stochastic gradient descent means one random example per update, which is where stochastic comes from. But in practice, everyone uses mini batches and just calls it stochastic. One sample at a time is just too noisy, and GPUs are built to parallelize over batches anyway. It just does many operations at the exact same time, making it far faster. There's one more idea worth introducing, and that is the idea of momentum. Plain stochastic gradient descent treats every step the same size. They are scaled only by their learning rate. But let's say a weight has been receiving tiny gradients for many steps. It's barely moving, even though it might need to travel a very long way. And let's say now that a weight is receiving huge noisy gradients, we risk overshooting. So adding momentum fixes both. Instead of using the raw gradient at each step, it keeps a running memory of past gradients. And if a weight keeps being pushed in the same direction, the steps gradually get larger. It builds up speed like a ball rolling downhill. If the gradients are large but erratic, they partially cancel each other out, and the effective step will stay controlled. Small gradient, big step. Big gradient, small step. And it is this on its own that can make the training process that much smoother, faster, and more efficient. Now let's put it all together. The loss function measures how wrong the network is. MSE mean squared error and MAE mean absolute error are two common choices. Mean squared error punishes large errors, and mean absolute error is more robust to outliers. Backpropagation then computes how much every single weight in the network contributed to that error. It does this by applying the chain rule backwards layer by layer from output to input, reusing intermediate results so it stays efficient. Gradient descent uses those gradients to update every weight in the direction that reduces the loss. The learning rate controls the step size, basically how fast we train it. We use mini batches for two reasons. First off is that the loss landscape is full of local minimas that can trap the optimizer, and more prominently, saddle points, flat regions where training just stalls. Random batches introduce noise that help to escape both. And it's also just much faster than waiting to process the full dataset before each update. Then we have the notion of momentum, which makes training more stable by building up speed on consistent gradients and slowing down the noisy ones. Run these three steps, measure, trace, and update thousands of times, and the network will learn. That's how every model you've ever used was trained. Same loop, same math, just scaled up. For those who made it this far into the video, thank you so much for watching. I do have a next one that will be coming out soon, which will be detailing the different use cases of neural networks and how to basically modify one to fit a specific task you want it to perform, right? Um, Although I can't guarantee when I'll have it out since I do have a few exams. So, like usual, feel free to leave any questions or suggestions you have in the comments, and I will see you in the next one.